And so a little bit about me. So I am a trainer, I'm a developer, I've written some books. You can find them in Amazon, and most of them, please buy them, and they make me money, so don't forget about that, just do it later. I have a few tools I have in my GitHub repo. You can again look at them. Mostly are open source, so just take a look. And there's of course my blog, which I write from time to time. Again, if you're having trouble sleeping at night, you can try my blog. Some people say it helps, so don't be shy. Okay, so what we're going to talk about is ETW. I'll start with a brief overview what ETW is, what it allows us to do, what are the components that comprise event tracing for Windows. And then we'll look at various tools, libraries, and code to see how we can use this powerful mechanism for our own applications that are usually related to diagnostics or profiling we want to do on our code, maybe on a machine that we don't control entirely. So let's begin. So what is ETW? ETW is a pretty old mechanism. It started its days in Windows 2000. Microsoft created something that provides logging infrastructure that should be powerful, should have some semantics, which means has some kind of manifest or some metadata that describes what kinds of events are available and what types, each property of the event, and so on. And it should be with very low overhead. So it is possible to have thousands of events per second using ETW and still not overwhelm the system. And still the CPU and I/O performance should be very good and only and barely noticeable. So these were kind of the goals for creating this infrastructure. So Microsoft created that for themselves. They actually needed that to understand what's going on inside Windows. Windows is a very complex operating system, a lot of moving parts at the same time, many services and kernel components, and it's really quite a big system. So what's going on at every point in time? Why is something working the way it is? Why is something not working the way it's supposed to? So ETW was created to try to answer these questions. And through the years, many providers were created that generated more types of interesting events, some of them by Microsoft, some of them by third parties. So actually anyone can generate and participate in that same system, which again makes it very powerful. And so one of the properties of ETW is that it's always system-wide. And so if you look at something like a debugger, if you try to debug something, you actually attach to a certain process. So you're attached to this process, you can see everything is going on in that process, but what about other processes? So you have to attach to more processes if you're interested in them, but sometimes you don't really know what's going on. You can't really pinpoint the exact process that may be causing you issues. And so you need a more holistic view, something which is system-wide. And ETW is always system-wide. So you always get events from everywhere, events you're interested in, and then you can go ahead and filter using some particular process you're interested in or something else. But it can give you some direction where to look next if you don't have a clue of what's going on. You're not sure which process is problematic in one way or another. So ETW can give you that holistic view. There are many providers that are available out of the box in Windows. You can just go ahead and type logman query providers in some command window, and you'll see a very long list, more than 1,000 providers that are registered inside Windows today. Each one of these providers has a set of events. Each event has its own properties. So there's really quite a lot of information that is available on any Windows system. Just need to tap it to somehow get to that information. And this is what the session is really about. So let's discuss briefly the architecture of ETW, all the major players that are part of this system. So we have something called provider. Providers are those that generate events. As I mentioned, there are more than 1,000 providers built into Windows, but in fact we can create our own applications that also are providers of events. So we can be part of the system. So providers sort of generate events. It's just a matter of whether there is someone or something that is interested in those events or not. And so providers generate events. And then we have controllers which allow us to create a session. A session identifies a set of providers that are kind of bundled together and configured in a certain way. So a controller can create a session, it can start a session, it can stop a session. So it's going to create a session and then just enable a set of providers into that session, saying which providers are interesting for what I'm trying to achieve. And so I need to take several or one or more of these providers into the session. And then I can start and stop the session. So what happens now is that these providers send events, and these events are gathered in some internal ETW mechanisms using some buffering techniques. And this allows this information to be gathered and then provided to consumers. So one way to do that is to target a file to be the target of all this information. This is an ETL file. This is the classic extension for this type of file. Then you can take this file and analyze it using various tools. I'll discuss briefly the tools available for ETW that you may be familiar with some of them. On the other hand, you can also have consumers that consume these events in real time. And so they're just there. They're going to consume these events and do something with these events. They can drop them, they can analyze them, they can store them somewhere because they want to know what's happening right now. Now, ETW has some disadvantages. One thing is, I think the most important one probably, is the fact that there is a short delay between the time of the actual event to the time the consumer actually receives the event. It's something between 1 and 3 seconds. And the reason for that is for all this buffering to take place with low overhead, there is some caching being performed by the ETW system. And so if something happens, you will know about it roughly 1 to 3 seconds after it happened. The information inside the event is still correct. So you're going to get the time that the event was raised, not the time you actually got it into your consumer. Now, in most cases, we don't care about that. We say, okay, fine, I'm going to get this information maybe 1 second or 2 seconds later. That's okay, I can live with that. There are some cases where you can say, well, maybe I can't live with that. In some cases, for example, in the cybersecurity world, if you want to know that something happened, such as a process has been created, you can listen using ETW. And then when you get a notification, maybe you say, that process is interesting. I want to open a handle to the process to get some more information. However, malicious processes in some cases are very short-lived. So they come up, do something probably bad, and then just terminate. So you get notification that the process started and then exited, but at that point of time, you try to actually open a handle to the process, that's actually too late. The process is already gone. So in some, I would say, corner scenarios, this is not good enough. You need something perhaps more powerful than ETW, but for most cases, for cases we're working with that are not related to cybersecurity, that's good enough, even if I get the notifications a few seconds after they actually happen. And so inside Windows, actually, there are already several sessions that are running on the system. So if you go to the performance node here, let me try to zoom in a little bit. So in the performance node, there's a performance monitor here. And by the way, performance monitor shows performance counters. So maybe it's worthwhile to discuss briefly the difference between performance counters and event tracing for Windows. So performance counters, I think the basic difference that performance counters are only numbers. You can't convey anything except numbers. With ETW, you can convey numbers and strings and data structures, anything that you want. Performance counters are limited to being just numbers, which I'm sure they're pretty useful in their own way, of course, but if you want something more powerful, I think ETW is that thing. And so I'm not going to look at performance monitor here, it doesn't really belong to this session. However, under this data collector sets node, there's something called event trace sessions. And this node actually shows you all the currently running ETW sessions on the machine. And in fact, if you are an administrator, you can even stop these sessions or even delete these sessions, because only administrators can actually create and manipulate ETW sessions. So of course, this would be probably a bad idea, because it's probably some application that is depending on this information being available, and if you just close that session behind the scenes, that application is probably going to have some issues. So you probably don't want to mess with that, but still you can look at the information, but look at the properties of each one of these sessions. You can see the list of providers, for instance, that are part of this particular session. I've just selected randomly, and you can see some more properties of that session, such as some basic filtering you can do and stuff like that. And in fact, you can add and remove providers. Again, if you're an administrator, you have the power to manipulate ETW sessions, which means you can also add and remove providers on the fly, and of course, stop and kill the session. And so we have more information here, for example, whether that's actually been written to a file or maybe it's in real time. You can see this is a real-time session. So there's some application right now on the system, maybe even a kernel component, that's fine as well, that is listening to these events and expect them to continue flowing and does something with this information. So you can take any one of these sessions and just take a look at what's going on under the cover. And once you actually create your own session, it will appear here as well, because this is just a global list of all the running ETW sessions on the machine right now. So something we can look at, and in fact, you can even, if you really want to, you can actually even create your own new session. So it is possible to do something like a new data collector set, which is a really weird name, but in fact it means let's create a new ETW session. So you can actually create that with a user interface here, add your own provider, set some properties, and the session is live. Again, if you're an administrator, you can do that. But of course, we'll be doing these kinds of things using code. Okay. So these are sessions. So how do you work with ETW? What tools are available to work with ETW? So several tools are available which are in-box inside Windows. The basic tool is called Xperf. Xperf allows you to start a session, stop a session, add providers to a session, really manipulate session. This is a command line tool, so it's not very convenient perhaps, but it's not too bad either. You can actually work with that. And there are some other tools to kind of help with these things, such as trace report, which allows you to kind of format the information that you get back. So let's say I'm using Xperf to record several seconds of events from providers I'm interested in into a file. So now I have this ETL file, so what I'm going to do with that file. And so it has all the information, but how do I get to it? So one way is using trace report, which allows you to create something like a CSV file from all the events that have been gathered into this ETL file. And so then you can open that in Excel, and well, good luck with that, because usually you have so many events that it's very difficult to kind of make sense of that if you're just looking using tools such as Excel or CSV file. But there are other tools. So for example, we have the Windows Performance Recorder and Analyzer. The Windows Performance Recorder is the tool that allows you to graphically start ETW session. It's installed as part of the Windows Performance Toolkit, which today is part of the Windows SDK. So here's what the tool looks like. What you need to do here is really select what kind of providers you want, but this tool is more high level and gives you some general descriptions of things you may be interested in, and it's going to activate the appropriate providers under the covers. So if I want to analyze stuff related to CPU usage, I'll just select CPU usage and let the WPR to enable the proper providers that would give me rich information about CPU activity once I actually start recording. And so this is just a convenient tool to actually initiate recording. You can also see there's a scenario analysis here which tries to kind of say if you have one of these issues, just select the appropriate checkbox and I will enable the most likely providers to help you diagnose this issue, which is, again, very nice. So once you press the start button and the recording starts, so again, this is system-wide. Once you start recording, then you can do whatever you need to do to have that scenario repeated if you are trying to diagnose some scenario. And then when you're done, you're going to just click the stop button. This will create the target file, and then you have to analyze that. So for analysis, there's actually a very powerful tool for these kinds of scenarios called the Windows Performance Analyzer, which is sort of the friend of the performance recorder. And it allows you to have some graphical view of events that have been recorded using WPR. But this is a generic tool that can analyze any ETL file, but it is very useful in cases where you have a CPU stuff, perhaps issues in CPU or memory or I/O or networking, then this tool can be very helpful to analyze these kinds of scenarios. And I'm not going to look at that because, again, I want to focus on actual programming and what we can do to build these kinds of tools, but there are many examples you can find on the web. There's another tool called TraceView, which is another tool that shows information in a tabular format. It is part of the Windows SDK and WDK. In fact, it started in the Windows Driver Kit. And again, another tool that allows you to select providers, run some sessions, and in real time see what's going on. There's the PerView tool, which I guess probably many of you know. PerView is a tool written by Vance Morrison, which is the performance architect for the CLR. And this is a tool that allows you to actually, again, record ETW events. It is more targeted to .NET related scenarios, but it is a general tool. So it knows more about the CLR because it looks for uses particular provider and knows how to analyze CLR stuff, but it is generic. You can actually record any ETW session with it, with the appropriate providers. There's one tool I've written called ProcmonX, which is sort of an alternative to the classic process monitor from sysinternals that uses ETW to get information about process, thread activity, I/O, networking, and so on. Whereas the classic process monitor from sysinternals uses mostly a kernel driver to get this information. And it's actually not really needed. And the focus of this talk is your own tools. So one thing we want to look at is how do we see the information that is available for the various providers. Let's say I have a provider. What does it give me? So as I mentioned, there are more than 1,000 these kinds of providers inside Windows. So how do I see what they have? And so I created a tool called ETW Explorer, which is a graphical tool that can show you what happens inside the provider. So if I open some provider, doesn't matter, I'm going to filter to some provider, such as Microsoft Windows Kernel process, whatever that may be, and click OK. And what I get here is a list of all the events that are being or can be generated using this type of provider. And then I can actually select a specific event and get the properties and their type that are available inside this event. So if I consume this event, there's a process ID with a 32-bit integer number. There's a process sequence number, which is a 64-bit number, and so on. So everything is here. And so once you have this information, some of it may be actually documented in the official Microsoft documentation. Some of it, or actually most of it, is not. But it's still relatively intuitive, and you can actually guess, in most cases, what the parameters mean. And then you can just use them in your code in a way that I'll show you in a few minutes. And so this is a useful tool to just see what kind of providers we have. So one more example, for instance, is .NET. So we have a CLR provider, which we'll discuss in more detail a bit later. So we can just select that and see what kind of events it has. So notice it has 168 events, such as when GC starts. So what kind of information do you get when a garbage collection cycle starts? So you can see here the information that you can get. And so it should give you an idea of where to look next, or what events may or may not be interesting for your case, what you're trying to achieve. So that's ETW Explorer. You can look at that. It's, of course, open source and available in my usual GitHub repo. So how do we work with ETW in terms of code? Eventually what we want to do is write some code. We want to use all that powerful mechanism in our own applications. And so one thing we can do is be a provider. This is not the focus of this talk, but you can be a provider. You can raise your own ETW events, which can be captured like any other ETW event by other consumers using a file or real-time session and all that stuff. So there's the system diagnostics tracing namespace that you can use for that purpose. And then there are consumers. So how do you consume these events? This is the most interesting stuff because there are so many events already out there. How do we actually get them to our own code and do some analysis or something with that information? So there are actually two libraries that you can use. The first one, and I think it's the most powerful, is a trace event library, which is actually used by Purview. So it was written by Vance Morrison, the guy that wrote Purview, and in fact Purview is built around this library. And it is open source and of course available through NuGet. And so you can just add it as a reference and just go ahead and work with it. And since it's a very rich library, you can do pretty much almost everything you can do with ETW, you can do with this library, which is very nice. There's another library that is called CRABS. CRABS is another, with a K by the way, it's another library that is from Microsoft. It is a C++ library that was created by Microsoft for its own internal use, but then it was open sourced. And there's a wrapper around it which is called Lobsters. That's kind of the, I think the sense of humor in Microsoft. So there's CRABS with a K and there are Lobsters. And so Lobsters is the .NET wrapper, which is built, by the way, using C++ CLI, and which allows you to take advantage of this library inside your .NET applications. So it's more lightweight, it's much simpler, but still could be useful because it's not that big. It's relatively simple, although the first library, the trace event library, is more fully featured. So I'm going to show you how to use both of these libraries in a few demos that are coming up. So let's start with a simple provider and consumer, just to show you how I can be a provider. Because in many applications, in fact, I would say in all applications, you need to do some logging. And maybe you're using something very, very simple like debug.writeLine or trace.writeLine. And the problem with that is, so first, debug.writeLine by default doesn't get actually produced in release builds. And even if you're using trace.writeLine, you're usually not really happy doing that for several reasons. One of them is performance. If you're using a lot of trace.writeLine, this actually has a performance hit because there's a bottleneck there. There's a lock that is taken every time you're doing that. And so it is slow, especially if you're using some multi-thread application that's doing a lot of trace.writeLine. This is catastrophic. You should never use it. It is best to use debug.writeLine for very simple scenarios during debugging. But if you want to do something in production, this is too slow. So using various libraries such as log4net and nlog and all those stuff, and some of these can actually provide or produce ETW events as part of their sort of way of outputting this information. And you have a schema here, which you don't have in trace.writeLine. This is just a string. You have no information about anything except that string. So let's see how that works. So here's an example of a provider. This is a provider. A provider just inherits from a class called event source from that namespace I mentioned earlier. I have to give the event source a name. It can be a string name or a GUID to make it has to be unique. Otherwise, there will be no way to distinguish that to perhaps another provider. And then I can just write a bunch of methods that actually raise the event using the writeEvent method, which is something I inherit from the base class. So typically what we'll do is have these attribute here called event, giving us some event ID and some more information we can specify, such as the level of the event, whether that's informational or verbose or warning or error and stuff like that, which is part of what ETW actually provides. It's not something we have to to invent it's already in the ETW infrastructure, and then just call write event as needed and expose an instance, some singleton instance of that object to anyone that needs it. So in this particular case, what I have is a very simple Windows Forms application, and this Windows Forms application uses this log to raise these events in various scenarios. So the point here is that I want to log something, I want that to work in production, I want that to be low overhead, so this is what I'm doing. And I'll be able to use the ETW infrastructure to capture this information. So let me first run this provider. That would be a simple provider, just run it. And I can click these buttons, so if there are no consumers and no one is listening, this just goes down the drain, so nobody cares, just goes away. However, if I now have myself some actual consumer, so my consumer is going to be a simple console application here, and that consumer, I'll show you the code in a moment, is going to get these events. Once I start clicking these events, these buttons, I should start getting notifications. Here we can see that every time I click something, I get some information here. So notice there's a show delay. That's the 1 to 3 seconds delay I mentioned at the start, but I'm getting the information. Here I have an event stream where I'm kind of sending many events using a thread pool, and you can see that these events include numbers, they include text, the exact same thing I've actually set here in my event source. So I can specify any type that I want, which would be part of kind of the schema this provider provides for its events. So I can just have this particular, in this case, just a simple consumer. So even if I close the window, I have some information. I'm actually sending another event. And again, I can call these write methods anytime that I want and not be concerned about performance or stuff like that, because EW is very fast inherently. So what would the code look like to actually consume these events? And so if we go ahead and look at the consumer, our simple console application, this is in fact using the trace event library, that one that Purview uses as well. So here's the basic steps of creating a session, adding providers, and then just using the information that we get. So here I'm creating a trace event session. This is a session object. And then I need to enable provider. So I can call the enable provider any number of times to enable provider based on its public name or a GUID, which identifies it uniquely. So I'm saying here's the provider name. This is the same name I used in the attribute in my provider class. I can even specify some more information, such as which level do I want to subscribe to. So maybe I want to subscribe to warnings and errors only. Maybe I want to see everything. So verbose really says, I want to see everything. Let me see any type of event. And then I need to use something called a parser. So the idea of a parser is a class that knows how to interpret certain types of events. So because we don't have any specific parser for this particular provider, we're going to use the most generic parser that is provided by the trace event library. And this is available using this dynamic property, which is something which is typed dynamic trace event parser. We can actually create an instance of that as well if we wanted to, and pass the session as a parameter to that parser. And because this parser actually knows nothing about the provider, it doesn't have any specific properties for that, there's only one event we can actually register for called all, which really just says anything that's going to come out of this session with all the providers enabled in it, just call this method for me, which is implemented here. And here we get an object which is of type trace event. This is the base class that represents any ETW event. And this is the most generic one. So some piece of information are inherently inside this object, such as the timestamp. So when did that event got raised? When did that provider actually raise the event? So I can see the timestamp here. I can have the ID of the event. That's the ID we actually set in the provider. we can have the process ID, the thread ID, and stuff like that. So these are generic information that we can have. And then, if we want to get to the actual properties, because this is a generic parser, it knows nothing about them, I just simply go ahead and look at the payload names, which are all the properties that are available for that particular event, and just write them out to the console. So one of them may be an integer, the second one may be a string, the third one may be something else. So in this case, I'm just printing them out, but in realistic cases, I know what to expect. I know that there's a property called, let's say, the event number, or perhaps some text. Then I'm going to get that property directly using payload value with a particular, or payload name with a particular string. And as we'll see in a moment, there'll be more parsers that are available in Box for certain providers that the trace event library knows about. In fact, we can actually create our own parsers, and I'll show you how to do that briefly later on as well. So once we have these things set up, we need to actually initiate the session to say, let's start working. And this is done using the source property here, which is the trace event source under the covers. We're using the process method. The process method doesn't really return, so it's a blocking method. So if I want to have my thread do other stuff, I should probably call this in a different thread. But in this simple demo, I'm just using the main thread for that. And so this actually starts pumping events. So whenever event is available, my whole event handler is going to be called. I'm going to do something with that information. So this is a very simple consumer, but in fact, most consumers look like this. So next, I want to discuss one special provider called the kernel provider. The kernel provider provides kernel-related events. So it's mostly about processes and threads and memory and networking and all that low-level stuff that may be interesting for any kind of application, not just .NET. I'm writing code in .NET to have my tools written in .NET, by maybe analyzing various types of processes. Some of them may be based on .NET, some of them may be native, and that's fine. So the kernel provider is kind of special. It has some special semantics. So for instance, prior to Windows 8, there can only be one session using the kernel provider. In fact, the session name must be a hard-coded value, which is called NT-kernel logger, and actually is available through a helper property that is provided by the trace event library. And most of the events inside this provider are semi-documented. So there's information in the official documentation, what each event has, what kind of properties it provides, and so on. And so the kernel provider is really powerful. It also allows you to do something like profiling. So you can get every millisecond information about what was running on the machine. And so you can do something like actual profiling of code to see where your CPU is at that particular range of time that you're actually measuring the performance. So let me show you some examples of using the kernel provider. So the first example I'll show you is about basic information I can get from the kernel, so the kernel provider, that is. So I have a console application here, and I'm creating a trace event session like before. And so this is again using the trace event library. I still have to show you something about the lobsters library, how to use that one. I'll show you that after this particular demo. And so in this case, I'm having a new trace event session and providing my own name if the version of Windows is at least Windows 8. Otherwise, I'm going to stick with the default name or let's say the mandatory name, which is available through this simple property from the trace event library. And here we can see there's enable kernel provider method. So normally, we have the enable provider method, which allows me to set any providers into that session. But for kernel provider, there's a special method that's enable kernel provider. And what I have to specify here are what keywords, or essentially what types of events am I interested in. So in this case, I'm going to be interested in process-related events, such as when process starts up, when process is terminated, and with image loads, which means when DLLs are loaded into processes or unloaded from processes. And the list is long here. there's a lot of information here. I'm going to show you another example a bit later that uses other types of keywords that are part of the kernel provider. But for kernel events, luckily what we have is a parser. So there is a built-in parser coming from the trace event library that knows how to interpret these events. And so when I try to register for events, I'm not registering for all. All is just too generic. Instead, I'm registering for the actual events I'm interested in, such as when a process starts up, when a process stops, when image is loaded, when image is unloaded. These are the 4 events I'm interested in right now. And of course, they're available because I've enabled these certain keywords. So in each one of these cases, just simply taking the information and outputting it onto the console. And then, of course, I have to call the process method on the trace event source behind the covers to actually start getting these events. So in this case, I'm going to actually do that on a thread pool thread using task run. And so I'm going to just sleep on my main thread for 1 minute to gather this information. So let's see what that looks like and then discuss a few more finer points here. Let me run that. And so I run it and things start happening. So I'm getting some image loads here. Let me just run something like CMD. So once I do that, I get many more events. So we can see CMD has been created along with conhost, and some DLLs already loaded into that process. And of course, this is system-wide, and I haven't provided any type of filtering, so this will continue in this manner. Let me just quit that, and you can see that conhost has exited, and CMD has exited. So I get these with these process start and process stop events that are registered for. And there's a lot of useful information in those events. And because I'm using a parser, these events, I can use proper properties. So the property for E here is not just trace event. It's a subclass called image load trace data. And it has parameters that are more than just the general parameters, such as the file name, or which image was loaded, and the size of the image, and some other pieces of information that are simply available because we have a parser that understands these types of events. So there are a lot of things here we can look at, again, depending on what this event actually has to give us. Another thing I want to mention here is the idea of state management. So let's say I have processes here. Maybe I'm listening for the process stop event. So if a process is now terminated, I want to give information about which process it is. So I have the process ID, but what about the process name? Can I get the process name? So actually there is a property called process name inside that trace event object, but it's sometimes just empty. It's sometimes empty because it's not really a property provided by ETW, by that particular provider, but it's something that is sort of generated or tries to be provided by the trace event library, but sometimes it's just not there. So how can I get information about that process that actually is gone? So because it's gone, I cannot handle to that. So what I need to do is to have some context. I need to save information. So what I started doing here at the first line in main, I'm actually looking at the entire processes on my system right now, and then just having a dictionary that maps a process ID to the process object, which is the ID and in this case, the process name, to some ID. Sorry, I'm using the ID as a key to a dictionary that handles these processes. And so when I try to actually look at the process name, instead of just printing the process name property, which sometimes is just empty, I'm using a helper here called try get process name. And I'm saying if the process name property has something, that's fine, let's just use it. But if not, let's go to my dictionary and try to locate that particular process and see whether I actually know about it. Because if the process is now terminated, it means it started at some point in time. So I have that in my dictionary, so I can find it using the process ID and then return the process name. So I have to kind of keep up with things that are happening. So every time process is created, I actually have to add to my processes dictionary this new information. Otherwise, I will not have it available. And of course, remove it when the process stops. So it would be a good idea to do that. So I have to keep up state because the events are disconnected from one another. I'm getting one event, then another event. How do I connect them? And so I have to maintain state. This is a very simple example, and I'll show you in a moment some more complex examples of that. So what about these lobsters thing? So many of you are probably familiar with a tool called Debug View. Anyone know about Debug View from sysinternals? So not that many of you, so that's bad. Go ahead and look up Debug View. So Debug View is a tool that allows you to look at output from debug write line and trace write line, and more generally output debug string from for applications, whether they are .NET or not .NET. And so it's a very useful tool. And one of its capabilities is also it allows us to look at or find or capture traces coming from the kernel. So for actual kernel drivers or the kernel itself. And the way Debug View does that is by installing its own driver that hooks the DBG print API, which is part of the kernel for doing these kinds of things. But actually that is not really needed because this information about these kernel events or kernel notifications or kernel trace is actually available through ETW using the kernel provider. And so here I have a tool I've written that is sort of a replacement for Debug View. So it has nicer icons, I think. But I can also capture kernel here, and I actually added the ability to capture user mode traces as well, just for fun. So it actually is a replacement for Debug View. But I don't care about the user mode capturing here right now because capturing user mode traces is not available through ETW. So I can capture kernel here. And so what I have here is a driver that I've written. It doesn't matter what it does, but I have some traces when the driver starts and when the driver stops. So the driver is called booster. When I click start, you can see we get here these two outputs which are actually being provided by the driver. And so I can capture them without having any of my own kernel drivers hooking something. I don't need that. Everything I received here is from ETW itself. And so I can now stop this driver, just unload it, and it has another output here that's saying that it has been unloaded. And so I did that using ETW with the crabs library, the lobsters library, if you will. Let me show you what that looks like. And so there's a lot of stuff related to UI here, but the main thing is this. First, of course, I have to get this from NuGet. So the library is called Microsoft O365 Security Native ETW. This is the lobster library. You can find it on NuGet. And then what I need to do is this. I'm going to use the kernel trace class. This is their class that represents kernel trace rather than a user mode trace. You can give it some name. And then I'm going to use a provider called the debug print provider. So it's actually, if you look at the trace event library, it's something that should be exposed there as a keyword. But for some mysterious reasons, the trace event library doesn't support the debug print provider. I think it's just something that Vance Morrison missed, or at least thought it wasn't useful enough because it is kernel stuff and unrelated to .NET. So he didn't create any wrapper for that. But we can use lobsters for that. So here's the provider. And what I'm doing here is enabling the provider. And before that, I'm just registering to the single event called onEvent that is going to be called whenever something is appearing using these providers. In this case, that single debug print provider. And once that happens, I can just look at the information I get from the event using an interface called iEventRecord. This is what I get. And as opposed to trace event, there's no parsers here. It's just a generic object that has sort of a dictionary that maps string properties to the actual values. So what I need to do here, I'm taking the basic parameters which are always available, such as process ID and so on. But if I want to get the actual message, for instance, I have to go to the get ANSI string method with the string message, because again, this is a late binding kind of way to get that information. That's because this is the way this library works. It doesn't have any concept of high-level parsers. I actually have to go to the appropriate property using this get something. So there's a get ANSI string, there's a get Unicode string, get uint32. There are many get methods here in that iRecord, that event record object here, so I can get any information that I need, but I need to know what to look for. I need to know what kind of properties are there for me to find. And again, this requires this schema using ETW Explorer, for instance, or some other documentation for that. This is just what I did just to show you that I can use ETW and I don't actually need a kernel driver to get kernel notifications. So next I want to show you another example which is about profiling. So profiling means I want to know what's running on my system, and ETW allows you to do that using the same kernel provider. So it has a keyword called profile, which what it does, it kind of generates information every 1 millisecond of whatever is running on the system right now. And so the event to register for is called perf info sample. Again, since I have this higher level parser, the kernel parser, there is a specific event for that eventuality. And so I have this information, just aggregate the number of samples, and of course I have to keep some state. So I want to know, for example, which processes were running the most code in the time or the time frame where I'm actually recording this information. So I have a dictionary here which is a samples per process. So each process is identified by a process ID and the process name. This is not actually super correct, but is good enough for this demo. The process ID only is not good enough because process IDs get reused. So a process can die, a new process can be created which has the same ID of that old process. That in fact sometimes happens, and so we can't use the process ID itself as the key. So I actually added the process name, although the correct way to go here is to use the start time of the process. So the start time and the process ID together are unique per machine for any process. And then I'm going to just count number of samples for each one of these processes. And so now I'm using the same kind of boilerplate code. I'm creating a session and then enabling the kernel provider with the keywords that I want, using the parser to register for the events that I'm interested in, and then simply just calling source process to start pumping events. That is it. There's nothing else here. In this case, I'm just sleeping for 10 seconds, but I could have stopped the sampling at any point in time. And once I get a sample, I have to check to see whether that process is already in my dictionary. If it is, I'm just going to increment the number of samples for that process. This is something that's happening here. If it's not there, then it's the first time this process has appeared in my dictionary, so I'm creating a new instance for that and adding it with a counter of 1 sample. So each time I'm going to get a call, I'm going to just increment that number, and then just print out some statistics when everything is complete. And so this is the statistics that I print here, which is just showing the process list of the most busy processes that have accumulated at least 1% of CPU time. So a lot of talk, let's see this in action. So that's going to be a simple profiler. So I'm going to run this, and for fun I'm going to add another process here which knows how to waste CPU time. It's a very, very powerful thing to have. So I have this CPU stress application that just knows how to waste CPU. Just eats CPU. It's very, very useful. It's very calming if you need something like that. So after 10 seconds, we can see that the sampling is done. We can see the list of processes that have been running in that period of time, each one with their consumption of CPU based on number of samples I've accumulated throughout these 10 seconds of recording, in a sense. So you can see the CPU stress is number 1 because it was working quite a bit, but other stuff was working as well, such as Visual Studio, which is very weird. I mean, I actually didn't run this with a debugger, so what is Visual Studio doing here? So that's very, very weird, but again, that's something Microsoft needs to answer, perhaps. And There's some other services here that are running, and again, maybe say, why is that? Why is Slack taking 1.5% of CPU when I'm not using it right now? I mean, what's going on there? So that's Node.js for you. Anyway, we can use these ideas to profile stuff. So again, sometimes we see things here we don't expect. Maybe we expect some process to use CPU and that is fine, but suddenly you see something else. Hey, what's that process doing here? Why is it consuming CPU time? Let me show you yet another example. Using, the same kernel provider. And this is an application called the Network Monitor. So sometimes I want to know what's going on from network perspective on my system. Which connections are open, how many data is transferred. So this may be useful in a particular system or in general on some machine. So what I have here is this kind of application that knows how to look at connections when they're created, number of bytes that have been received using TCP or UDP, and I can just filter these things out depending on what I want to see. And for each one, I can see the remote host using its address, and even do some reverse DNS to look at the actual DNS name. And so all this is actually available through the kernel provider, through the keyword related to networking. All I need to do is actually just say that I want it. And so every connection that is actually being closed, I can also look at the number of the amount of time it was open. Okay, so for every connection. So in this case, I'm not doing a lot of networking activity right now, so nothing special is happening too much. But in fact, there is some UDP activity here by a process. Some of them is SVC host, some of them some other process that all the time doing some kind of connections to the outside. Let me show you how to build something like this. So again, the basics are very similar to what we've seen already. And again, I need to have some state management here, because let's say a connection has been opened. And now I'm going to get some bytes received or sent through that connection. I need to kind of correlate that to the original connection, because the event itself has no particular affinity with the early event. It just says, hey, this is the local port, this is the remote port, this is the number of bytes, that's it. It doesn't know how to kind of correlate with the previous connection that was open. I have to actually keep track of it myself. And that's why I have more dictionaries to do all these things. So what I have here is a dictionary that maps a connection key to something, to a connection, which is actually hosted in a different collection, which is called active connections. So I have active connections. These are the actual lines you see in the UI. Each one of them is actually an object, of course, that has the information about the connection, when it was started, how many bytes have been received, to what remote host it's connected to, in what port, and so on. Everything is that's needed inside this network connection class. And so once I have a connection that is open, I'm going to add it to the dictionary, and then when I have something like a receive or a send event, I'm going to correlate that with the open connection and add the received number of bytes to that object. And so these things are dynamic, and I have to actually keep track of these things. So how do we do that? So again, it's going to start in exactly the same way. I'm going to create a trace event session, and then just enable the kernel provider, in this case using the keyword network TCP IP, which means I'm interested in network-related events. And so now I have to register, because again, I have this nice parser, high-level parser, that knows how to interpret these events in not just using the all handler, but something more specific, and say, okay, when we have a TCP IP for v4 connection, let's call this method. For IPv6, let's call this method. So I'm just registering for a bunch of events related to what I'm interested in. So I'm interested in connection starting, connection disconnecting. I'm interested in when bytes are sent and received, and just have my own handlers for these cases. So for connect, for instance, I'm creating a network connection object with some initial properties based on information I get from the event. Notice that because I'm using this high-level parser, I'm not getting just a trace event-based object, but something which is more powerful, more full, has more properties that are related, such as the remote address, the remote port, the local address, local port, and so on. and just adding that to the list of connections that I have. And that add connection method is also adding that into the connection map. So I'm getting some key which is based on the process ID and based on the remote address and local address, and add that to the dictionary and get that association that I can use later on when I actually get another event related to the same connection. So a lot of work is actually being done for maintaining proper state. So the actual work of starting the session is pretty easy. There's nothing different between that and the previous example. I'm just enabling the kernel provider, setting up events, and then eventually just calling process on a different thread so my UI thread doesn't block for processing these events. And this is really it. So most of the actual work is what to do with this information. How do we process that or store it in a useful way? So here I'm using some UI, but of course you can think of other tools that do some analysis and understand why am I connecting to that server? Why is that taking so long, or maybe not so long? Why am I only passing 20 bytes? Why am I passing 2 megabytes, which I wasn't expecting to actually happen? And so all these things we can get, and it's unrelated to the actual process you're interested in. It could be a native process, a .NET process, it doesn't really matter. Okay, so that was about kernel events. So I mentioned the idea of parsers. So the trace event library from Vance Morrison provides several parsers out of the box. One of them is for the kernel provider. There's another one for CLR-based events, which we'll look at in a moment. And there are actually some other parsers in there. So what happens if you want to create your own parser? So the classic way is just to say, okay, there's a base class for all parsers, so I can derive from that, and then just do some fairly boilerplate code to map generic events to specific events to have my own wrappers. But fortunately, I don't actually have to do that. There's a tool provided by this great Vance Morrison called Trace Parser Gen, which allows you to take an XML manifest, which can be generated using the ETW Explorer I've shown previously, and actually generate a C# code file that already has the parser built in it from the metadata read from the XML file. So it's pretty easy to do. So if I go ahead and open my ETW Explorer here, let's look at some other provider. Let's do something like the Windows battery. Apparently, you probably didn't know that, but the Windows, there is actually a provider called Windows battery that provides information and events on what happens to the battery, whether it's charging, not charging, connected to something, not connected to something. So if I go ahead and click OK, there are in fact several events related to this battery. And so if I want to get information about the battery in my system, ETW is really a great way to do that. And so I can look at every event and so on. And so if I want to currently now use it, I can use the generic dynamic parser and just register for the all event and just have everything there and try to kind of figure out what's the event ID and then go to the correct property and so on. But a better way is to actually go ahead and save the XML manifest. Let's call that battery.xml in some folder. And then all I need to do is just call trace parser gen with the file. And what I get back is a battery.cs file, which is ready to be included in my talk, in my code. Okay, so apparently I'm out of time. So what I didn't show you is stuff about the CLR provider, which allows you to see information about, for example, exceptions, GC events, many stuff that is there. And so the demos I will not have enough time to show you, but they will be available in my GitHub repo after this talk, and some interesting stuff in there. So just let me summarize what we've seen. Another thing that I did want to show you but didn't get a chance to is that you can actually get a call stack capture of every event. And so you know how you got to that location, such as when you have a throw statement, you want to know who is the one throwing the statement. why is that actually happening? And so OTW is a very powerful mechanism you can use to understand what's going on in a system and in your applications. Thank you.